So let's get started with that. Okay. Now analyzing a periodic pulse is sort of, can be done. It's not difficult, but a better thing to start with is
the u of t you mentioned.
Exactly, the unit step function.
Yeah.
Because something goes up and then it stays.
Yeah.
And we are trying to see how lazy this capacitor is, how lethargic it is, and how much time is it going to take to catch up with this voltage.
Yeah.
And therefore, we are saying we are giving it infinite time. And we'll see, okay, how long do you take? When do you catch up? This is what we want to study. Okay. So I have an input V in of t. Specifically, I am going to say V in of t equals u of t, the unit step function. It's going through a resistor R1. I can call it R for all practical purpose. There's no second resistor.
Okay. And C.
And C. And this output I am going to call as Vc of t. Vc of 0 minus equal to 0. Okay, that means it's completely discharged. So how did you solve the, you and Ani did this KCL, KVL. So does KCL, KVL hold if I have a capacitor, by the way?
It's voltage only. Every instant it should be valid.
Exactly, right? So for every instant, KVL must be valid, right? So therefore we can simply write the, so this is, by the way, the plus and minus, right? So what we are saying is we are going to go around this loop and write the KVL. Okay. So let's say that V in of t, right? The current through this resistor is I. Okay. It's a function of time.
Yeah.
Okay. I times R plus Vc of t.
Yeah.
Right. So at every instant, right? I think I will also explicitly say this is a function of time.
Yeah.
At every instant of time, this equation must be valid. Okay. Now I have two variables, I of t and Vc of t. What do we do?
Maybe one of this we can represent using the other one.
Exactly, right. So the current through this, the KCL tells us that the current through the resistor has to be the current through the capacitor.
Correct.
Because it's going through, right? And what's the relationship between the current
in a capacitor?
Yes, and the
I think
voltage.
It is a C dV by dt.
Exactly, right? dV C by dt.
Yeah.
So this is, this is what you call a differential equation, and we need to solve this in order to understand such a system. So V in of t equals R into C dVc by dt, okay, plus Vc of t.
Yeah.
So now we have a variable which is Vc of t that we want to solve for as a function of time, and we have a nice differential equation of this form. Okay?
And V in of t after 0, it's a constant.
It's a constant. So V in of t, as we had plotted earlier, is just going to be like this. It will be 1 after it is 0. Before that, it's going to be 0. This is the u of t function, right? And that we will substitute that later, okay? And u of t, so for all practical purposes, we will just assume that this is 1 volt instead of 200 millivolts, and it can be 1 volt, it can be any amplitude, it really does not matter, okay? Now, how do you solve such a differential equation? Okay, first of all, we have to look at what is it that we can solve in differential equations. The only equation that we know how to solve is dy by dx equal to f of x. Suppose we are given such an equation, then all we have to do is dy equal to f of x dx, and then I can integrate both sides, right? So I'll get y equal to integral f of x dx plus a constant.
Okay.
Right? This we all know from 12th standard, right? So we have to first, whatever differential equation we are given, we have to reduce it to this form. Okay, so what is the differential equation we have? We have dvc by dt. So actually the t is x here, right? That's the independent variable. 1 by rc into vc of t. Okay, I'm just dividing by rc.
Okay.
Yeah, and I'm going to say v in of t by rc.
Sure.
Right? This is what we have.
Yeah.
I will therefore rewrite this as dvc by dt plus p times vc of t equal to q of t.
Okay.
Okay, both p and q are functions of t. Right? So now how do I do this? I am going to now simply write this as, I will multiply by e power integral p dt on both sides. Okay, because I need to get it down to this form.
Okay.
Only then I know what to do, right? So I am going to multiply by e power integral p dt. So just bear with me as to why I am doing such a weird thing.
Sure.
Okay.
As long as I get some answer, I am happy.
Yeah. So e power integral p dt, okay, into dvc by dt plus p into vc, right, into e power integral p dt is equal to q of t into e power integral p dt.
Yeah.
Okay. Now there's an advantage here, right? If I look at this and I just look at d by dt of vc of t into e power integral p dt. If I look at this and do it by parts, okay, and I mean do the UV rule here, right? I will get vc of t into derivative of e power integral p dt plus e power integral p dt, okay, into d by dt of
VC
of t. Now this is just e power integral p dt, okay, chain rule, p dt into d by dt of integral p dt.
Okay.
Plus e power integral p dt into dvc by dt of t. Okay. Now this is nothing but p because it's derivative of an integral.
Yeah.
Right. So therefore, this term that we had here, this term I can simply replace by d by dt of e power integral p dt into vc of t.
Okay.
So now you will see why I did all this jugglery. I can write it as d by dt of e power integral p dt into vc of t equals q of t into e power integral p dt. Now this is of the form that we know, dy by dx equal to f of x, and I can just take the dt to the right hand side and integrate.
Okay.
Right? So therefore I will simply get e power integral p dt into vc of t equals integral q of t into e power integral p dt dt.
Yeah.
There's an integral on top in the exponential and the integral below plus a constant. So this is what we need to use now in order to solve our differential equation that we have here. Okay. So let's just go back now and look at what is our p of t. our P of t was simply 1 over RC. It's a constant.
Correct.
Okay. Q of t is 1 over RC into U of t, the unit step function.
Yeah.
Right, and the equation we had was dVc by dt plus P of t into Vc of t equal to Q of t. Therefore, I will now go ahead and apply this solution that we got, e power integral. So, let us look at what is e power integral p dt first of all. Okay, implies e power integral p dt is e power integral dt by RC. So, this is nothing but e power t by RC.
Okay.
So, this is just one term, okay, and then we said the solution to this, by the way, let us just write that down, e power integral p dt into Vc of t equals integral q of t e power integral p dt dt plus c. Okay. So, this was straightforward, we just got as here.
Yes.
Implies e power t by RC into Vc of t, okay, equals integral q of t, by the way, for us is 1 by RC into u of t, e power, what is this, t by RC dt, okay, plus a constant, right. So, this is what we have. So, now how do we go ahead and solve this guy? Okay. So, u of t is essentially like what? It is just a constant, right? It is just a constant, and therefore, you can have e power t by RC into Vc of t equals 1 into e power t by RC dt, right. So, I have 1 by RC into e power at integral dt is just 1 by a. So, it is 1 by RC, right, e power t by RC plus a constant.
Yeah.
Right. I think this makes sense. So, the RC will cancel here, which implies Vc of t equals the e power t by RC, I will just divide on both sides. I will get 1 plus C e power minus t by RC.
Oh, because divided.
Yeah, you have divided. Now, how do we find the C?
C is initial.
Yeah, exactly. So, C is a constant, we need to find out, but remember that is the reason we made this initial condition. Capacitor was initially discharged,
Okay.
right. So, therefore, you come here and you say, simply substitute. So, you have, sorry, now I can switch to blue, okay. 1 plus C e power minus t by RC, okay, and Vc of 0 minus equal to 0. So, just substitute t equal to 0 in this equation, you will get 1 plus C because it is just e power 0, implies C equals minus 1. Therefore, Vc of t is going to be 1 minus e power minus t by RC, right? Great. So, we will have to analyze this equation and see if it fits what we observed and stuff like that.
So, at least the output we had, it was not a straight line, it was not triangular.
Straight line, right?
So, we were mentioning there is some smooth shape.
There is some smooth shape and stuff
so
like that.
So, that kind of exponential shape
Exactly, something
Was
like that
there.
seems to be coming out at
Good,
least.
good.
Okay. Now, what happens if this u of t was not to 1 volt? What if it was some a times or VGG times some number, right? In our case, we are 200 millivolt.
Yeah.
Then the equation would simply become Vc of t equals VDD or Vm. You wanted to use Vm, right? Into 1 minus e power minus t by RC. So it would, that's instead of 1, we are getting Vm there. Okay. So let's now.
So Vm is the voltage the square wave has.
Yes, a square wave has
when
or
it is high.
Exactly, right. So instead of the unit step function that was going to 0 to 1, suppose it went 0 to Vm, then what happens is what we were looking at. Okay. So now let's go back to our observations, intuitive observation. You made one observation about the value at infinity. So at infinity, you said it will just follow the input, right?
So is that valid here?
Let's check that, right?
Great.
So what do we do? Limit t tends to infinity of Vc of t.
Yeah.
So if I substitute e power minus t by Rc, right? E power t by Rc goes to infinity.
Correct.
So 1 by e power t by Rc goes to 0. Therefore, this is Vm.
Oh. So that's satisfying.
That is indeed true. So if you give it enough time, the capacitor is indeed going to follow the input and it will reach the input. Okay. Now, technically, this is going to happen only at t equal to infinity, because for any other real number of t, if you see, this e power minus t by Rc is going to be some small value. Okay, and it will be slightly less than Vm. Okay, it's going to be slightly less than Vm. So now, if we were to plot this output, how do you think this curve will look like?
So I can see the exponential part,
right?
So when we start, there is no voltage.
There is no voltage, but
finally
eventually
it is reaching Vm.
It is reaching Vm, but at any finite time, it is not at Vm. Just like going to be below Vm.
It is Vm minus
some delta, right? And what happens to that delta? At lower times, the delta is large. At higher times, the delta is smaller. So therefore, we have to, this is what you call an asymptotic charge up, right? This is called asymptotic charging. Okay, asymptotic means it never reaches that final value at finite time. It will reach limit t tends to infinity, it will go there. But for all practical purposes, 1 volt or 999 millivolt doesn't matter. For us, it's practically 1 volt. Okay, that's how we get away in real applications. So let us now look to plot this both V in and V out, just like we saw in that thing, right? So like that
same
plot
color
that we saw, I'll use the same color. Okay, I'm going to use, for V in, I will use orange. So it is basically, 0 till t equal to 0, then it is going to Vm. Okay. Now the blue is my Vc of t. For before 0, it's going to be 0. At infinity, somewhere here, we know it's going to follow this
Vm
and it will merge eventually. What happens in this period? Now that's probably why we should go and look at this waveform. We'll also look at the waveform to get a picture. Okay, so I gave what? Maybe 1 kilohertz, let me give it. So this is the thing, it starts at 0, it's getting asymptotically to
the final value,
200 millivolt that we have given, but in between it's a smooth continuous curve.
It's an exponential curve.
Yeah, it's an exponential curve like this.
Oh. So the mathematics helps?
Absolutely, it's the theory indeed does, validate the practical observation that we make. Okay, so therefore, I mean, it's clear now. We can also quantify certain numbers, how long, for example, because, we said it's an asymptotic number, right?
So we were saying if it's a different resistor, the
Yes.
behavior may be slightly
Exactly.
different. Now suppose if I reduce the resistor value,
Yeah.
what will happen to this curve?
So we'll come to that. So where is the time, what is it that actually quantifies the time in this circuit, right? That's not yet clear. So we saw that if you wait till infinity, it takes, certain,
Correct.
right? Now, at what point will the capacitor reach Vm by 2? Right? It seems to,
So we
because
can
that
equate
seems
and
to,
find.
that seems to happen if you look at this, right? Let's look at this. Vm by 2 is what? This is some minus 200. By the way, in this case, it's just so happened that we have applied a negative voltage also.
Okay.
Doesn't matter.
So then we can look at when it reaches 0.
0, right? Actually, it reaches 0 very quickly,
Yeah.
right? And then it takes a long time to go. That's the nature of this exponential charge up. Okay. So let's look at that. How do we find out? I want to find out time at Vc of t equals Vm by 2. So what should we do? We take this expression that we got
And
simply substitute,
yeah.
right? So Vc of t equals, let me call this instant as t1.
Yeah.
Okay, Vc of t1 is Vm by 2, that is equal to Vm into 1 minus e power minus T1 by RC. T1 by RC, right? Therefore, you rearrange these terms, you will get the Vm goes e power T1 minus T1 by RC equals half. I am just subtracting this half from this one, implies T1, if I now take ln on both sides, it will be RC into ln of 2. Ln is obviously log to base e, right? And what is this number, by the way? T1 is 0.693 RC.
Okay.
So this is where your question comes. Now, had you used a different RC, what would have happened? It would still take infinite time to reach the final value. So there's really no information there for us. But if you used a different RC, okay, the charge up could be faster,
okay,
like this, or
slower.
Exactly, or it could be much slower.
Okay. So the R and C values decide.
Exactly, not just R and C, it's the product of RC.
Correct.
That will decide time, and dimensionally ohm into farad is seconds, is time. Okay, so therefore it all of this makes sense together, right? And therefore, let's also go back and look at what was happening, right? Why did this appear to be like a triangular wave at some point? At some point, this looked like a straight line. Now, how is that possible? Okay, so let's go back and try to explain that a little bit now. So now we have this. Okay, I'm going to plot as a function of time, and so it's important to understand what this RC number is now. Okay, in this experiment, we used 1 kilo ohm into 10 nanofarads.
Yeah.
Okay, this was 100 microseconds.
Yeah.
Okay, that means this circuit is operating in a time scale of 100 microseconds. That means it would take 0.693 into 100, right? 69.3 microseconds is what it would take to reach 100 millivolt.
Yeah, half of the voltage.
Half of that voltage. And then it would take forever to go all the way there, right? So essentially, this is 100 microseconds, and what we have applied there, right? So earlier, by the way, when we applied a 100 hertz wave, right, we basically said the input was going to be orange, right? We said this 100 hertz. What was 100 hertz? It was milliseconds. 10, this was 10 milliseconds. Right? And this was therefore 5 milliseconds. Now, compared to 100 microseconds, this 5 milliseconds is like infinite time, right? It's very simple to see that. You just take this equation that we have again, okay? Vc of t, okay, is Vm into 1 minus e power minus t by Rc, okay? And I am looking at Vm into 1 minus e power minus t by 100 microseconds. Now, when I look at 5 milliseconds by 100 microseconds, it's a very large number. E power minus that effectively is like 0, right? And that's why when we gave this 100 hertz,
it was not so visible.
Yes, it was not visible. In fact, the waveform was like this, right? It would go all the way. Now it wouldn't fall abruptly. That is also going to discharge, right? So it falls like this. But effectively, 5 milliseconds is infinite time for this circuit.
Correct.
Because of the RC values, right? And that brings us back to that earlier question. What is low frequency? What is high frequency? It depends on the RC number.
Time constant.
The time constant, exactly, right? This is what you call the time constant. Okay. Now, we tried something more adventurous. We said increase the frequency, and we said, you know, we wanted to do this at some really fast frequencies, okay?
Basically shorter time periods.
Yes, shorter time periods. So we said now we are going to look at 1 kilohertz, right? Is that what we had? No, we are looking at 10 kilohertz now, right? We are looking at 10 kilohertz, and what is the time period? It's 100 microseconds. Okay, it's actually back to the time scale of that, it's a time constant of that RC circuit.
Yeah.
Okay, so this is like okay, this is what, 100 microseconds? That means this is 50 microseconds, okay? And we were trying to look at what is going to happen to that RC circuit, okay, whose time constant was 100 microseconds. Now, to reach VDD, VM by 2, we said it took 69.3, 70 microseconds.
Yeah.
So, if you look at this guy, at the maximum value, right, at 50 microseconds, which is where the half period is, it cannot go beyond 70, the swing cannot be over 70 millivolt, right? And therefore, this thing is what, starting at minus 50 and it's going up to
plus 50.
So it's going up to 100 is going up to, wait, one second, I just blow this up so that we get a better, okay. So what are we getting here? Sorry, so to go to VDD by 2, it could not do it in 50 microseconds. In 670 microseconds. So that is VDD by 2 is the 0 here. Right? So that is, so it's able to do us only a part of that cycle. It's actually trying to charge up. It is trying, if you look at this.
So maybe we can avoid this negative side of the input.
That also we can try. If you want to do that, let's see if there is a way to do this. I'll just give an offset. Right? Of
100 milli.
100 milli, right?
And then make the VM 100.
Okay, amplitude, offset, okay, is this right?
Yes.
Okay, so there is, it's like 0 to 200, and there seems to be some sort of a, yeah, it's around this 100 millivolt now.
Yeah.
Right, so it's charged up to some value,
Correct.
and then around 100 millivolt it is sort of, right?
Correct.
So that's what is happening.
So here it has a C.
Yes.
That integral.
Correct.
I mean, every cycle, that initial
Value. So
Yeah,
exactly.
yeah,
So what is happening is, initially it started from 0.
Yeah.
It was able to charge somewhere here.
Yeah.
And then
Started
discharging, right? Like this.
Yeah. Yeah.
Somewhere, not here, maybe
Slightly. Yeah.
like here. Then again it goes up.
Yes. Yeah.
Right? And effectively this exponential curve in that time scale is looking linear. So if you do a Taylor series approximation of that 1 minus e power minus t by rc, it would look like a 1 minus t or t by rc kind of equation, right? And that's why this is resembling a straight line. It's not a straight line actually, it's an exponential approximated as a straight line, right?
So when the input is 0, it's actually discharging to the source.
Yes.
Correct?
Yes.
So there the final voltage will be 0.
Exactly, it's trying to get to 0. So if I for example had a capacitor that was initially charged to 1 volt, and then I grounded the resistor, it would exponentially discharge down to 0 as Vm into e power minus t by rc.
Okay.
That's an exponential drop, right? So that's an interesting point. So the capacitor, if you look at it, right? So you apply a step voltage, you give it certain infinite time, it is charged to that maximum value. Now that voltage is actually available.
Yeah.
Right? We call it a passive element, but actually it is able to store that voltage for you.
Yeah.
And we'll see later when we do switch capacitors that you can actually switch that energy to another circuit
and do many more things.
And do many more interesting things. But ultimately the key takeaway from the lecture today is the time constant of the RC circuit is what determines the frequency analysis in general. There is a delay of the order of the time constant of the circuit, and therefore it's very evident now that if I have even one capacitor sitting somewhere inside my amplifier, the gain cannot be independent of frequency. It has to depend on how fast that capacitor can charge and discharge in order to give you that amplification.
Also, even this simple resistive divider that we mentioned.
Yes.
Any resistor that we take also has some parasitic capacitance.
Exactly. And again, the fact is the capacitance, the parasitic capacitance as you mentioned may be very small, but at very high frequencies they start acting up.
Yeah.
And therefore even an ideal resistor is not an ideal resistor.
It is acceptable as an ideal resistor for some range of
frequencies. Some frequencies that we operate in, it's an acceptable range.
Yeah.
Right? It's an acceptable ideal resistor. Otherwise,
so that is why you were saying if you apply gigahertz, etc.
Exactly. Right?
You may not get the same behavior.
Exactly. You said that from your experience at gigahertz, it's not going to give you the amplification. Why? Because of this.
Interesting.
Okay. Right?
Great.
So in the next lecture, we'll actually look at the sinusoidal response of an RC circuit and understand how that behaves based on this understanding. Thank you.